The lecture 26, we are going to begin with a review of the ADI method that we have discussed so far and talk about the choice of acceleration parameters, namely those Peaceman, Rashford and Workspace methods. We will talk about Gersh-Gorin's theorem that identifies various disks where the eigenvalues reside, and once we know the eigenspectrum, we can find out this acceleration parameters, and in a further expansion of the idea of ADI method, we point out that this is essentially an additive splitting and works only for 2 dimension. When we go to 3 dimensional problem, we do not have the ability to use the ADI method, and then also we find that on many tough problems ADI methods do not work, and we move to a new class of method which are called the multigrid method. Essentially the idea here is to work on a set of grids, not necessarily on one grid like what we have done so far. And in the context of multigrid method, we can fall back upon the classical iteration as the constituent of this multigrid method, and that is why we reinterpret the classic iterative method in terms of the eigenvalues and eigenspectrum. And as an example, we begin with discussion with 2 grid method. That is essentially we are talking about one coarse grid and one fine grid, and introduce the various operators that are involved in solving multigrid method, namely some of them are mentioned here, restriction operator and the injection operators. We did talk about how operationally it is done. You do not need to look at all the eigenvalues to reduce the error. What you do instead, you strategically position some acceleration parameters between the minimum and maximum, A bar and B bar, and then this number of such strategically positioned acceleration parameters are obtained either by Varga's suggestion or the one that is given by Workspace. And we presume that these parameters would provide us with a very high rate of convergence. And we did talk about a theorem which happens to be a very handy tool in finding out the maximum and minimum of eigenvalue of any matrix, and that is due to Gersh-Gorin. And we actually use that Gersh-Gorin theorem 1 to obtain the disks which are nothing but symptomatic of the entries of the rows or columns of that matrix A. And what you do is that the disk has a center which is given by the diagonal element, and the radius of the disk is given by the sum of the modulus of all the off diagonal term in that row or column, and you assemble all this disk. That gives you the kind of idea of the spread of eigenvalues of that matrix. Okay. So, this is how one does, and going with the theme of iterative solution of elliptic PD, suppose we are trying to solve, and suppose say for the sake of understanding, assume that we are working on a Cartesian frame, and we have, let us say, non-dimensionalize the problem in such a way that we can take the range of x and y from 0 to pi. Okay. If we do that, then error vector could be written in terms of the eigenfunctions taken from the Fourier modes, that sin I is the x direction node number, j is the y direction node number, and the amplitude is given in terms of capital E with a superscript n inside the bracket. Then you realize that the step we followed in ADI method involved taking the solution at nth level and then just simply solving it in the with the h parameter, and that would take us the solution to the half step n plus half and this ut term would be nothing but then u n plus half minus u n by delta t by 2. So, what we can do is we can really substitute 72 in this equation. Okay. So, basically if you do that, what you are going to get, for example, if I write this down, that would be as given by 72, I would write it as E sub superscript of n plus half, that is the amplitude. And when I am doing the x derivative operation, the y dependent part remains same. So, this path sine pi j q k would remain same. So, k is basically delta y. So, k is delta y and h is delta x. And so, if I now write this, so this is essentially the operator is we know it is something like ui plus 1 minus 2 ui plus ui minus 1. So, this is the form of the function. So, that basically would So, what happens then, this would then become n plus half, and this we keep it as it is by j q k, and this 2, if I add it up, I will get 2 sine pi phi into cos. So, basically I can pull out this factor, and then I will get 2 cos pi ph minus 1 into, minus 2 into sine pi phi, right? And of course, I could write it somewhat taking a factor out. So, I get 2 e n plus half, and this part and that part are symptomatic of what we began with. This will be 1 minus this, that will give us itself 2. That is why I put a minus sign here to absorb the changing quantity here, 2 sine square pi ph by 2 into sine pi phi and sine pi q k j, and that's this operator, right? So, this is what we have written it down. So, that is this expression, and the second one would similarly you could just simply write del y square u I j, and that is n, will give us something similar. So, I will write it as 2 e. Now, this will be at the next step, and y operation would give us 2 sine square pi q t by 2 and this same factor. Okay, and the right hand side is easy for us to find out. That will be simply En plus half minus En by this, and you can open it up and simplify it. This is what you are going to get. Okay, so from here we of course I have not written down that part. I have written it with h square. So this is with the square I have written. So I have just taken that. It's divided by, right? So So this is divided by h square. So I'll just simply look it like this: h square into this and k square into this, and then substitute in this equation. Simplify. This is what you are looking at. So basically, R1 and R2 are something like our Peclet number in the x and y direction, right? That's what you are seeing. That R1 is the Peclet number in the x direction, R2 is the Peclet number in the y direction, and you find that the amplitude by which the amplitude changes in the half step is given by this factor: 1 minus 2R2 sine squared pi qk by 2 divided by 1 plus 2R1 times sine squared pi h by 2. Now, this has a form of this kind, right? 1 minus a square divided by 1 minus 1 plus b square. And since a and b are dissimilar, so there is no way you can make any observation about the value here, right? It could be less than 1, it could be greater than 1, it could be anything, right? This factor that we have written here, it could be anything. However, in the next half step, you would be doing something like this: delta x square u and j. We will take it as the previous step, but now we are going to do the next half step that will be taking us to the end of the step. So that's what we are going to get. And this side we will get uij n plus 1 minus uij n, and that will be divided by delta t by 2. Okay, so that's the second half step that we have not written down, but that is implied. And you go through the same kind of substitution of the error vector that you have provided here, and do the calculation, and you would see that the amplitude ratio in this half step works out to be almost identical in nature. It looks like 1 minus b square divided by 1 plus a square. So overall, actually, the total step would take you from En to En plus 1. So you just simply multiply these two factors and you get this. This is exactly like what we said about the similarity transformation, that eigenvalue does not change, and in the end what you get, that individually these factors are not guaranteed to be less than 1, but the compound step, the product of the two, gives you these factors, right? 1 minus a square divided by 1 plus a square, and this second is similarly 1 minus b square divided by 1. So basically, this is what we actually conclude, that in ADI what we are doing, that individually the steps could be unstable, like what we just now explained. However, when we put them together, we get a stable algorithm, right? So that's the key to success of ADI method. Now, this was possible because we are looking at a two-dimensional problem, and the operator that we had, we could split it additively, and we could do those things so symmetrically the error cancelled out to give us a stable method. For 3D problem, we really can have the same luxury of straightforward applying this procedure. We may have to do a little additional manipulation. So additive splitting does not really work out as easily as it was for 2D. That is one thing that we observe about ADI. And there is another thing that you have noticed, that when we worked with ADI method, we chose those acceleration parameters, and once we chose those acceleration parameters, we stayed with it in the same grid, right? We kept on working with the same grid, but we kept on changing the acceleration parameter to reduce the error. Now, there is a parallel work that was done in Russia in the late 50s by a mathematician named Fedorenko. Fedorenko actually is smart enough to notice that when we are doing all this iterations, like if you recall, we worked out all those expressions for G1, G2, G3, G4, G5. What did we find? That as we went along, it became progressively worse and worse. And in the fifth step, actually, the ratio overshot by 1, right? So Petrenko's observation was that if we keep doing any kind of iterative operation, what happens is the first few steps are pretty much optimistic steps. It reduces the error very rapidly. Then it stops. Why does it stop? If you now connect that point DI method, you would see that as you went along, you kept on working on different eigenvalues. And your iteration number increases means your eigenvalues are going up in the list. So what happens? Initially you work with the error which have much larger wavelength. They are controlled easily. G2 also is the next harmonic, and G3 will give you the next harmonic, and so on and so forth. But by the time you have come to the fifth harmonic, things have started misbehaving. That is exactly what we noticed. So the idea was that it's probably then not worthwhile to keep on struggling with the same method, which we know is doomed to not yield any good dividend, right? It is going to get worse and worse. So how do we improve it? So his observation was that the errors, those which are reduced, had some relationship with the size of the domain and the way we discretize. Those errors which are of the size of the domain, they decrease faster. That's what we saw in G1, G2, etc. But the moment we kept on going into higher harmonics, there it was no more good. So this was noted very smartly by Petrenko, and he suggested what is now called as multigrid method. Now I have often told you about this word. I probably never wrote it down. Eponymy. You know, when somebody does the work, somebody gets the credit. Petrenko did it and wrote it in his thesis. Nobody knew about it. Then there was the smart American mathematician R.Q. Brand. He comes out in the 80s. He notices all this. He gets a similar idea. He says, okay, we have a new method called multigrid method. So in the multigrid method, the idea is the following. That's what we are trying to show you by an example. Let's say we are trying to solve a trivial problem. Of course, we can analytically solve it, right? But I'm just using it just to demonstrate how it works. What you do is, suppose I have to solve this ODE, a one-dimensional problem, in a small, in a domain, one-dimensional domain between 0 and 1. Let's say we have the Dirichlet condition provided at the end of the domain. Then what we do is we keep on working on different types of grids. Because every time I work on a particular grid, I know which are the error components which are going to be damped. So the moment I exhaust that possibility, I go to a different grid. And there I start working on a different wavelength of error component, right? What is advantageous in this sense? It is advantageous in the sense that if I am working on a coarser grid, of course I am doing less work, lesser number of points. But the moment I decide to, like in a ADI, I kept on working on the finest possible grid, right? But this is where the distinction came in multi-grid method. That you may start off with a fine grid, but then you can keep on migrating to coarser and coarser grid, and then you can go through this process in a sequence, right? In an iterative sequence. Every time you exhaust the possibility of error being reduced in that particular grid, you go to the another grid. That's where the name multi-grid comes from, okay? You work with multiple grids. So of course, you know, Eponymy is the story. Petrenko did the work, but it flourished in the 80s with a lot of effort from R.Q. Brown and many other mathematicians all over the world. So what we do actually, let's say we have the domains between 0 and 1. So the least possible discretization that you could do is this, right? Having one point in the middle. So then the spacing is 1 by 2. I think that is it. mistake. This should be H1. So this is our initial grid. H0 is half, right? The spacing is half and half. Then we reduce the spacing by factor of 2, and then I get the spacing will be 1/4. Then I go to the third one, that will be 1/8, 1/16, and so on and so forth. So this is the way. There is a typing mistake. So this should be H1, H2, H3. So we take the sequence of grids such that the spacing has this hierarchy. And the number of points, of course, have been taken to be given by HL. It's, let's say, LX level grid we are looking at. The number of points is given by 2 to the power L plus 1, right? That's what we are getting, right? H0, H1. You can see that. And then, of course, the spacing is 1 over 2 to the power L plus 1. So at any nth level, we can talk about a grid given by the set. We'll write it as omega L would be nothing but nu times HL. Nu is the counter of the points. So if I have the spacing as HL, I will have HL, 2HL, 3HL, all the way up to NL minus 1 into HL. Okay? So this is the idea. Now let's understand why we need to work on multiple grids. So what I do is I just simply discretize that equation that we started off in solving. So what we get is basically a second derivative of u with respect to x. We write it like this. Now if I define the grids at the nth level, let's say we are working on the nth grid, so that's why we are using the subscript L here, and there is the forcing function F. Then this is the discrete equation, right? Good purpose, we chose it because it's easy to follow. It gives you a tridiagonal matrix with a strictly diagonal dominant property, and what we do is try to understand what it is. So basically the discrete equation that we would have would be something linear operator operating on the u at the nth grid level, forced by this forcing term FL. And then if I look at any one line in this discrete equation, so if I write the corresponding eigenvectors as G, so this is nothing but minus G. So the diagonal term will be Gm, so 2Gm, and then minus G m minus 1, and this will be minus G m plus 1. And since we are trying to find out the eigenvalue of this matrix, so that would be nothing but this eigenvalue equation, right? Ax equal to lambda x, right? That's what we are written here. So that's what we are written. Ax equal to lambda x, and then we wrote any one of the line, that would be this. Now you understand, the diagonal is m, so we have a super diagonal plus 1, subdiagonal plus 1, and the diagonal itself is minus 2, and because we have on the right hand side minus lambda into Gn, so put it on this side, so we get this, right? We have a periodic problem, right? That's how we say. So if I am the Dirichlet condition problem. So what I could do is I could write down any arbitrary solution in terms of a complete set, and let that complete set be the Fourier set. So if I do that, I can take this as the basis function, right? Sine of this. So I am actually looking at the number of points in the n direction is given by capital N. So that's how I'm doing. I'm dividing pi by n plus 1, and then with two indices m and k will identify the modes, right? So we are looking at the mth row, so that's why the n is there, and k is the one that we can, even for that single row, I can have all possible eigenvalue combinations for k ranging from 1 to m. Okay, now you can substitute this and work out, you will find the eigenvalue is this. Exactly like almost similar to what we have done here. We write down, substitute there and simplify. We find out that the eigenvalues are this, or this equation, right? And the eigenvectors, of course, this is the chosen eigenvector that we have. So if I now look at this equation, ln ul equal to fl, that had the 1 over hl square outside. So that's why the eigenvalues of the ln matrix is given by minus 4 by hl square into sine square phi nu hl by 2. Now, if I think of very simple, let's say Jacobi type of iteration, then what I do usually is I write down the L operator in terms of a diagonal part, and anything that is other than the diagonal entry is written here as d of L. Okay. So if I substitute this into ln ul equal to fl, this is what we get. Right? So in the actual iterative sequence, what we do is basically we put the left hand side at the new level, right? J plus 1th level of iteration, and this right hand side we keep it at the previous level J, and then the Jacobi operation would imply that I will take the simply D inverse, right? The diagonal entry. That's what we have done also some model example of 3 by 3 matrix, because that's the way we do. So the Jacobi iteration would be nothing but taking the diagonal part out and using that to define the n matrix we talked about. So you actually write it down, so BL inverse, and BL itself is nothing but minus of LL into LL minus DL. So if I carry out this operation, BL inverse inside, I will see that this is the way actually point Jacobi iteration works, that whatever we have at the new iteration level is nothing but the old iteration level value minus DL inverse. So this is your n inverse into the defect. This quantity we call it as defect. We have also defined something called residue, which is nothing but minus of defect. So it's all that. So basically what we are seeing that at every level we end up obtaining a correction. Correction is uj plus 1 minus uj, and that is driven by the defect and driven by the choice of the matrix. That's how we do. This is something well known to us. So, but we also have seen that sometimes we could actually increase the convergence rate by under relaxation, introducing this factor capital theta here. Since it's under relaxation, we keep it between 0 and 1, right? That's our definition of under relaxation of this class of methods. And for the problem that we have chosen, D inverse is nothing but HL square by 2 into I matrix, right? That's what we do, because the diagonal entry is minus 2, right? So if I take D inverse, that will be minus 2 by HN square already is there, so that goes in the numerator, so I get D inverse as HN square by 2 into identity matrix. And so this has a half factor here, so theta by 2 if I define as omega, so I will write down this under relaxed Jacobi method as the new iterate is equal to the old iterate minus omega HN square into this effect. Okay, so that could be written down in this particular part, right? ML times the old matrix. So ML is nothing but our iterative or the amplification matrix that we have already defined. Okay, so how well this method is going to converge will depend upon the eigenspectrum of this M matrix, and M matrix is given by I minus this. So we have already found out the eigenvalue of LM matrix, so it is not at all difficult to find out the M matrix eigenvalue. That will be nothing but 1 coming from this I matrix minus this quantity, omega HN square, and the lambda of the LM matrix, which itself is 4 by HN square sine square phi HN 2. So basically what we are finding, the eigenvalues are given in terms of this. And this we have often commented that we choose theta, capital theta, or in this case omega, so that to hasten our convergence. And so if I choose, let's say theta is equal to half, so theta equal to half will give me omega as 1/4, right? And if I take theta equal to 1, means no relaxation at all, that will give me omega equal to half, right? Because that is theta by 2, right? So what happens is the eigenvalue of the matrix, the spectral radius, as we call them by rho. So rho for theta equal to half will be nothing but maximum of this sequence, 1 minus sine square pi mu HL by 2. So what will be the maximum? The maximum will be when this is going to be the least, right? Sine square part will be least. That will correspond to mu equal to 1. So we get this 1 minus sine square pi HL by 2. And if HL is small, I could see that this is the spectral radius, right? So this is what we have commented upon earlier also, that the under relaxed Jacobi method, actually the spectral radius varies with HL square. So what does it mean? That it means that you can solve the problem with a coarser grid, right? The moment you go over to a finer grid, what happens? HL comes down and your rho comes closer to 1. That means your error reduction ability comes down, right? So if you work on a finer grid, you will find it much more tougher to convert. So this so happens that people have historically found out initially, with the limited computing ability, we used to take 20, 30 points and show some good results. The moment you have a better computer, instead of taking 20, 30 points, you take 200, 300 points, and immediately you see that the convergence history has become very worse. So that comes out from this observation, you can see, because the spectral radius is directly proportional to HL square, and if HL becomes smaller, so HL square becomes even smaller, so your spectral radius is very close to 1, and you don't get any benefit even for this modern simple equation that you have. Whereas if you look at the case where you don't have any under relaxation, it is 1 minus 2 sine square pi HL by 2. So if I, instead of reading all that, let's go over to this next page and then we'll see what we are talking about. Like when we take theta equal to half, omega equal to 1/4, my eigenvalues are given like this, right? I could plot on this axis mu times HL. So if mu times HL is 0, so then I'll have a maximum case, right? Sine square 0. So I will have the eigenvalue as 1. But as the eigenvalue number index increases, it keeps on changing its value, and we have seen it's 1 minus sine square mu pi HL by 2. So when I'm going to 1 here, mu HL equal to 1, so that will be pi by 2. So 1 minus 1 will be 0. So what happens that that may show here, that if I am working on this particular level of grade, then the different eigenvalues corresponding to the error behave differently because of the associated eigenvalues that I see here. The ones, those which are small, they do not change very much, whereas the eigenvalues which are to the right extreme, they are going to be damped very, very strongly because they're coming close to 0, right? So what happens is, I could mark out a space where I say, okay, this part, the shaded part, is the area where I get a very strong damping starting from half to 0. So every time I do that, my error gets magnified by this eigenvalue, right? So this part struggles, it does not change very much, but this part attenuates at a quite rapid rate. Okay. What does the large value of mu HL imply? in terms of wavelength. These are very, very small wavelengths. So what happens is, whenever we do this classical iteration, in the initial few steps, we keep on removing this small scale error very happily because of this nature. However, if you look at the case where you actually did not do any under relaxation, that corresponding lambda would be this, given by this red line. Why? It is 1 minus 2 sine square pi nu HL by 2, right? So what will be the range? It will go from +1 to -1, and that's what you are seeing. So if you don't under relax, then what you are seeing that it's only some intermediate stage where error is reduced. Even this size, you know, the error would not be reduced. Why? Because it is close to -1. See, your ability to reduce error will depend on how far away you are from 1, close to 0 in magnitude. So what happens is that this is a funny case that you are not under relaxing. So in the process what we do is we can control errors which have large wavelength, size of the domain given by this side, right? At the same time, we are not able to control the errors which are the smallest. Which are the smallest for a given domain and a given grid? It will depend on the grid spacing, right? We have already talked about Nyquist limit, so we know that the moment I choose HL, which is the maximum wave number that I can control, is given by the Nyquist limit. So if I don't do this under relaxation, I end up reducing error in the middle. My high wave number and low wave number errors remain sort of recalcitrant. They just refuse to change. Okay? And whether you are under relaxing or not, in both the cases you see what is the troublesome area. Troublesome area is this end. This end corresponds to the largest wavelength of the problem that you have, right? The domain size. That's what this corresponds to. So that variation, so if I talk about my domain by this horizontal line, those ones, those eigenvalues there corresponds to, I have showed you my 3 possibilities. The black line corresponds to the largest wavelength that you can handle with the grid. That is half the wavelength, right? Half the wavelength. The next one, of course, is the red one. That is the next harmonic that spans the whole domain by a single wave, right? And the blue line is something like a subharmonic, right? It's 3 by 2. But I could also have drawn the second harmonic and so on and so forth. Now, if you look at the error components drawn as we have done here, now what we are seeing that in this part, you know, this black error, which is positive, could be cancelled by this red component, right? But that is not so in this range. See, the region I have shown, region 1 to the left of the vertical line, is where all these error components are conspiring together to add, right? They are all adding up. So it's a very, very interesting situation, that why we don't want to do this kind of normal mode analysis and feel good that, okay, I am taking care of one harmonic at a time. But that's not the way the error behaves. Error appears together. So if I would have taken any arbitrary error, after say few levels of iteration, what I find that in this region, in this part, all of them add up. So I get a kind of errors peaking up in this region. In the other part, it has some mutual cancellations and it does that. So even though we are talking about a linear problem, where I would legitimately demand that I could superimpose the solution, but unfortunately the error shows that its distribution, spatial distribution changes because of this kind of a property. Okay, so error reinforcement in region 1 is very, very much of a possibility. So, what we then find is that we can draw these conclusions that we have written, that compared to omega equal to 1/4, omega equal to half has a better convergence. Why did I say that? Well, go back to the figure. What is the most difficult thing to control? The most difficult thing to control is in this region, right? And in this region you can see that red is better than black, isn't it? So red is what? That is without any under relaxation. So that's what we say, that when we look at the convergence history, we might see the solution without any under relaxation would do better than the one done with this. Whereas we have also noticed that with the under relaxation, what we are able to do, we could remove the error component which was at the highest wave number range, right? So what happens is, this is the crux of the second point, that for mu HL greater than or equal to half, the error is very effectively damped for the under relaxation case. Okay, so that's what brings us to the dilemma. I mean, we cannot afford to stay in one grade and then keep on working with different theta. That's what it means. See, the difference between these two tells us about how different theta does, and that is exactly what we are doing in ADI. In ADI, we are not keeping a fixed theta. We are those are those acceleration parameters. We kept on changing them, and we are trying to see what happens. And this is what I always, as I jokingly say, it's a poor man's blanket. I mean, you try to control the error on the high wave number, the low wave number is not controlled, and if you try to control the low wave number, you can't do it if you decide to stay in the same way. Now, this is what we learned, that the smaller wavelength, that is high wave number component area, reduces by at least half, but longer wavelengths are very slowly converging. And this is a practical experience. If you go ahead and try to solve the elliptic equation, you will always come back after some attempt and say, look, initially things look very good, error reduced, but then after some time it has stopped changing at all. And that is the story, that's what we narrated here. So basically the error, the iteration improvement that we have given by the last equation is actually dictated upon by this defect term. And now, so what we can do? What we can do is, instead we decide to work on multiple grids. So let me try to explain the whole thing with the help of only two grids. So one grid, let's say, has a spacing HL that I call as the fine grid, and another grid which will be twice the spacing. So that will be a coarser grid, I'll call it as HL-1. So the way that we would be working on would be, we start with some kind of a old guess that we are calling as U of superscript old. Then what we will do, we will do some small number of iterations in the finest grid itself, at HL level itself. What will happen? That we have seen that we could, if we do under relaxation, then we can remove those high wave number component. What does the high wave number component do? So if I have a solution and if you look at the low wave number component, it goes like this, right? The high wave number components will be riding on it, and if they are smaller than this, then you are going to get something, right? So this is let's say the total error will be given by this jagged line. So that jagged line implies that you have low wave number as well as high wave number components. Now, the moment, if you recall what we did here, moment we did few iterations in that grade, we are removing this part of the error. So what will happen? This will actually, after a few levels of solution at HL, this variation, this high wave number variation will go away, and I will get a rather a kind of a solution like this. So this I could call it by say U old, and this is what let me call it as U bar. So this is at the LF level. So this is what we have down here. That we start off with some initial guess, perform some small number of iterations at HL level, and then we get a smoother solution, right? So now you can understand this UL bar that we have obtained. It has smeared out on those high wave number variations, right? So what happens is, if I now, what we are trying to solve, is L of QL. Now this is also grid dependent, the operator also depends on the grid. So that's what we are trying to do. So it's an exact solution. We will be able to write it as level inverse. So that's what we have. So the exact solution is given here in this fashion. And then what I could do is I could construct a departure vector or error. I call it as VL. VL is nothing but the smoothed out solution minus the original solution. So what happens is, if I have done that operation, then this VL is a lot more smoother than what we had begun with. Because now having done all this iterative method, we have removed the higher frequency, so it becomes smooth. That's the whole purpose. Now, having obtained UL bar, I can calculate the defect. Because if you recall, the defect is what drives the solution. That's what we wrote in the last term, right? The defect term actually drives the solution. So what happens is, we calculate the defect, and then we try to solve for the new unknown VL in that, let's say, the finest grid itself. Then this is like this. So VL itself is UL bar minus UL. So that is nothing but a defect. So what happens is, now we need to solve actually this equation for VL with a defect which is a lot more smoother than what we had corresponding to U1. Now, if it is already smooth and we are already in the fine grid, doing anything more is not going to help me. What I could do actually, instead now I could go over to a coarser grid. See, basically this kind of smoothing at this scale, say if I look at this scale corresponds to what? HL. See, this corresponds to, in that figure we showed the right extreme points. Those are the maximum wave numbers which we could handle given this grid size. So that's what we are suggesting now, that look, we have exhausted all the possibility whatever we could in the HL grid. So now let's do that. Instead of solving LB equal to D in the L grid, we go over to a coarser grid. So what happens is, now I will try to reduce error in what? In this range, where the grid spacing is 2 times HL, right? That's our coarser grid definition. So what happens is, having exhausted those errors at the smallest possible level with the finest grid, we migrate to the next coarser level grid, and that is what is given here. Now, how do we solve this equation? Solving this equation requires the knowledge of this defect at the coarser grid. Now, what we do is we define the defect in the coarser grid is equal to R times dl. What is R? R is some kind of an operator. So I have the defect in the fine grid dl. I could have just, because the points are common, right, between the fine grid and the coarse grid. When from the perspective of the coarser grid, the points are common with the fine grid, then I could just simply pick it up. If I do that, that is what in mathematical jargon is called trivial injection. I just simply take it and put it. See, when things are very simple, we try to confound everyone around by jargon. So this is mathematical version. They will say, do not use trivial injection. I'll tell you why. But instead they say that you do this. Instead what you do is whatever may be the error that you have obtained in the fine grain, you take a combination of that at say x location by picking up the value there, add up its two neighbors and scale it so that you get equal to 1. And you know what has happened. Well, I think we'll discuss it tomorrow and then we'll see what actually we did.